Good morning, everyone. Hope you are all safe. This is Nayak sir from the Department of Mathematics. Now we are going to start with our online classes for your third semester course. From the Department of Mathematics, as we are offering this course Transform Calculus 4-year series and numerical techniques. Today we are going to start our discussion. First, let us know about the topics that are given under this title. As usual, there will be 5 units, and unit number 1, numerical methods. In this unit, you are going to study forward and backward differences, Gregory Newton forward and backward interpolation formula, divided difference formula, Lagrange's interpolation formula, and central differences. So, till this semester, you have studied what are the analytical methods that are discussed in your mathematics course throughout your PU and first year BE, and also your first to 10th standard. So all that methods are analytical. Now you are going to start a new journey, that is about numerical methods. There is a small but very important difference between these two, analytical and numerical method. Analytical method always gives you exact solution if the solution exists, otherwise it gives no solution. So analytical method has only two possibilities: either you get exact solution or no solution. But numerical method, given any mathematical problem, you can always find a solution, but the solution is approximately the or almost near to the exact answer. You may not get exact solution, you will get approximate solution. So it gives solution for any mathematical problem. Next, numerical differentiation and integration. We have already studied what you mean by the differentiation and integration, and what are different techniques to find the derivative or integral of the given function. Now we are going to find the derivative or integral of a function at the given particular point using numerical methods. So again we have a difference between these two. Usual differentiation means that gives the derivative of the function at any point. Suppose you have f of x equal to x square. Now differentiating that, you will get f dash of x equal to 2x. That is the derivative of x square at any point. If you substitute x any point corresponding to that, you get its derivative. But numerical differentiation means we will find the derivative of f of x at the particular point x0. Similarly, numerical integration, we are going to find the integral of a function at the given particular point x0. So in the second unit, we will discuss what are the different methods to find the derivative or integral of the given function using numerical techniques. Unit 3, 4-year series. So in this unit, we are going to discuss what you mean by Fourier series of a function and how to find the Fourier series of the given function. We have already studied Taylor series expansion in your first and second semester. In the first semester, we discussed Taylor series for a function of single variable. But in the second semester, we extended Taylor series concept for functions in two variables. So we have studied Taylor series expansion of a function. Now it is a somewhat higher version of series expansion. So Taylor series of a function that is used to express the complex function in terms of polynomials. Now in Fourier series expansions, we are going to write down the complex function in terms of trigonometric functions sin x and cos x. Taylor series expansion of a function exists only if the given function has continuous derivatives of all orders. Otherwise, you can't find the Taylor series expansion. Similarly, there are some conditions to check whether Fourier series of the function exists or not. So let us discuss what are the conditions and how to find the Fourier series expansion of a function, everything under this unit, unit 3. Next, unit 4. Here we will discuss Fourier transforms and Z transforms. We have already studied Laplace transform. I hope you people have not studied due to COVID-19 because it was scheduled after the first internals. So these concepts are almost similar to Laplace transforms. Laplace transform is basically a function that transforms functions from one domain to another domain. Same thing is going to done here under Z transforms, and both Laplace transform and Z transform comes under Fourier transform. So basically Laplace transform, Z transform, Fourier transform, these are all functions or mappings which carries functions from one domain to another domain. That's about Laplace transform, Z transform and Fourier transform, details of which will be given in this unit. So finally, unit 5, we have partial differential equations. We have already studied what you mean by partial differentiation and how to solve partial differential equations. Now we are going to discuss how to form partial differential equation. There are different methods by direct integration, by eliminating arbitrary constants, and involving derivative with respect to one variable, separation of variables, Lagrange's linear PDE. All these techniques are going to discuss under this unit, and in that we have applications of PDEs. So there we are going to discuss wave equations, ET equations and boundary value problems, how to solve such equations, that we are going to discuss under unit 5. So the textbooks are Higher Engineering Mathematics by B.S. Grewal, Advanced Engineering Mathematics by Krizet, and these are additional books for your reference. Glenn James, Advanced Modern Engineering Mathematics, Peter O'Neill, Advanced Engineering Mathematics, and B.V. Ramana, Higher Engineering Mathematics. So these are the textbooks that you can refer to study these concepts, whatever I mentioned in the previous page. Now let us start with our actual discussion. So now let us start with Fourier series. We have divided the complete syllabus as two parts, part A and part B. Now I am starting with part B. So here we are going to start with Fourier series, unit 3. Then we will discuss Fourier transforms, and then unit 5, formation of partial differential equations. Now let us start with unit 3, introduction to Fourier series. So first of all, we have to recall what we mean by Taylor series and how the Taylor series expansion of a function is determined. And basically we should have the idea of the functions, how a function is defined, how it can be represented graphically, and what is the importance of the function, why we use functions. So that idea helps you to understand the concept Fourier series more easily or more informative. So functions. So the definition says a function is an assignment between two sets. Suppose you have two sets, set A and set B. A function is just a rule that is made to assign every element of set A to elements of set B. So imagine the situation, you have two sets, set A and set B. Let us go with the example. We have here A equal to the collection of first 12 integers 1, 2, 3, 4 up to 12, and the collection B is the collection of months of an year, January, February and etc. December. Now I have a collection A and a collection B. Collection A is of numbers, collection B is of months. Now I can map with usual thinkings. 1 will be mapped to January, 2 will be mapped to February, 3 will be mapped to March, and so on. This rule will continue. How we are going to map this? So here, if you take generally, if x being an element of A, if you take f of x in this example is going to represent number of that month. How the months are kept in order. So first we have January, then it comes February, then March comes, then April, and so on. So in that order we are going to map this. So 1 is going to map on first month of the calendar, 2 second month, 3 third month, and so on. So generally for any x in this set, for any x in the set A, f of x is going to denote the number of the month. Sorry, it's an opposite direction. Month of that corresponding number it is. So we have f of 1. So month corresponding to 1 is January. F of 2, the month corresponding to 2 is February. So that is the rule which helps to map elements in set A to elements in set B. F of x equal to the month of corresponding number x. So that rule is called function. So basically it's a function is a rule or an assignment or mapping or correspondence. So there are many names for it, that maps exactly one element of B to each element of A. Single element of A can never be mapped to two elements of B. But two elements of A sometimes may map to same element of B. For example, you can take f of x equal to x square, the function f of x equal to x square. Then f of 1 is 1 and f of minus 1 is also 1. And this set we call domain, from which set we are going to pick x is domain. The collection of f of x is called codomain. So if f is a mapping from set A to set B, then set A is called domain and set B is called codomain. And for every element x of A, the element f of x which will be in B is called, f of x is called image of x under f. F of x is called image of x under f. Now think of one more example. Here I have given one example, and think of one such example. Let it be with the usual one. I mean, here I have given the example of month and number, and similarly try to formulate an example on your own. Don't give a mathematical example like f of x equal to x cube or x power n and so on. Give a real time example. Next, we have a function, but we need to write it down in some manner. So we need the representation mode for that. So how to represent a function? So there are many ways to represent the function. So in standard form we use these three. So the first one with a diagram. In the first circle, it consists of all elements which will be mapped to another elements. So this will be the domain, and this will be the codomain of F. So this is one way of representation. Another way is this one. Here we'll write the elements of A, here we'll write the elements of B. Then if A is mapped to this element, then we'll write an arrow, so that a member of capital A is mapped to a member of capital B. So similarly, we'll write an arrow. So see here, so two different elements of A have mapped to single element of B. This can happen, but two single element of A can never be mapped to two elements of B. That should not happen. Now this one is graphical representation. So we'll take here the elements of domain. Here we'll take elements of codomain. Now corresponding to each element of domain, we will map that to element of codomain. So we'll get a graphical representation. This graphical representation is most useful for our discussion, whether it is Fourier series or Taylor series. So this is about representation of functions. Next, types of functions. We can divide the functions into different types based on different categories or different conditions. Here basically we'll consider two types of functions, even function and odd function. To say that the function is even, it has to satisfy the condition f of minus x equal to f of x. That means, given a function f of x, if I replace x by minus x, then it should give same value. Both elements x and minus x should be mapped to same one. If the function is even, then its graphical representation will be like this one and this one. So if the function is even, then its graph will be symmetric to y-axis. See, this graph is symmetric to y-axis. Whatever you get on the right plane of y-axis will be reflected in the left of plane. If f of minus x equal to minus f of x, then we call that function as odd function. If the function is odd, then its graph will be like this. It will be symmetric to origin. So we have here the graph of some part of the function. So same thing is reflected, which is symmetric to origin of the plane. So these are two types of functions, even function and odd function. To say that function is even, just you replace x by minus x. If after replacing x by minus x you get the same f of x, then function is even. You get minus f of x, then the function is odd. Simple examples we have given here. So if f of x equal to modulus of x, then the function is even. Because even if you replace x by minus x, you get f of x only. If f of x equal to x, then the function is odd. See, f of minus x equal to minus x, which can be written as minus f of x. Similarly, f of x equal to x power n. If n is even, the function will be even. If n is odd, function will be odd. That is the general example.